Hey, welcome everybody. The following video will describe for us a mnemonic to help remember the primary function of parietal cells, which basically serve two really important purposes. Number one, acid production, and number two, the release of intrinsic factor, which is essential for B12 absorption. We'll also talk about B12 absorption, but first, let's look at the mnemonic, parietal cells et al. Now, the thing that always threw me off about this was the et al part, implying that the parietal cells may serve additional purposes outside of acid production and the release of intrinsic factor. And I don't think that's necessarily true. And if they do have other purposes, I don't think you need to know about them for board's questions. So here we go. The P and the A of parietal stands for produce acid, and parietal cells secrete acid. It's that simple, hydrochloric acid, and this results in a highly acidic environment causing protein denaturation. And also, hydrochloric acid results in the activation of pepsinogen, which is an important enzyme in protein digestion. So this is all about protein digestion. Next, we have the R and the I of parietal, and this stands for release intrinsic factor. So the second main function of parietal cells is to release intrinsic factor, which is essential for the absorption of vitamin B12 or cobalamin, whatever you want to call it. And the final part of the mnemonic et al, it's supposed to refer to the other functions of the parietal cells, which for all practical purposes is nothing really. So all you really need to know is that parietal cells produce acid and release intrinsic factor. The acid production is crucial for protein digestion, and the intrinsic factor is crucial for vitamin B12 absorption. All right, and next we're going to look at B12 absorption, and this is the pathway. You have to know this because there are many consequences when things are not going right. So it's a busy diagram, so let's break things down one by one. So first, we have B12. So B12 comes from the diet. So the foods that are high in B12 include the following: fish, meats, eggs, poultry, and milk. So as you can see, this can be a problem for vegans. Now, I'm not a vegan, so I'm not really sure where they get their vitamin B12, but it's not from any of these sources. Next, we have the R protein, and this comes from the parotid saliva. Yes, believe it or not. So R protein is made in the saliva, and as we swallow, it comes down and enters the stomach and the GI tract, and it binds to B12, protecting B12 from gastric acid. And here we have intrinsic factor. This is a glycoprotein that binds to B12. And although it's produced in the stomach, intrinsic factor doesn't actually bind to B12 until the duodenum, when B12 is no longer bound to R protein. So remember, R protein is bound to B12 in the stomach. So here we have pancreatic proteases, and this is how R protein is degraded. And it's degraded in the duodenum. Finally, in the terminal ileum, we have intrinsic factor B12 receptors, and that's going to be the end point, the end game for B12 absorption from the gut. So let's go through the pathway. Here we have the B12 coming from our diet. We have the R protein coming from the parotid saliva, and the two join together, and the R protein protects the B12 in the stomach from gastric acid. But then, when you get into the duodenum, the pancreatic proteases degrade R protein. And now you can see that the B12 is free to unite with intrinsic factor, and that occurs in the duodenum. And the B12 and the intrinsic factor complex travels down the duodenum, the jejunum, until they get to the terminal ileum, where they are uptaken by B12IF receptors. And B12 is released into the systemic system. Well, actually, the portal system first, right? And that's basically it. That's the entire pathway of B12 absorption. So as you can imagine, there's a lot of steps here, meaning a lot of things can potentially go wrong. So knowing this, I think we gain a lot of important knowledge that we can use to apply to our board's questions and to our patient care. So let's try to apply this to a board-style question. Here we go. Now, which of these conditions is associated with B12 deficiency? Chronic pancreatitis or celiac disease? B12 deficiency is seen in both. So both conditions, celiac disease and chronic pancreatitis, can lead to B12 malabsorption, not to mention fat, and fat-soluble vitamins also. And how does chronic pancreatitis lead to malabsorption of B12? So, prior to the attachment of B12 to intrinsic factor, the R protein has to be digested by pancreatic enzymes. I'll say that again. Prior to the attachment of B12 to intrinsic factor, the R protein has to be digested by pancreatic enzymes. Once the R protein is digested, B12 and intrinsic factor unite, and later they get absorbed by the terminal ileum. All right, so hopefully you all got that question right. So in celiac disease, you get atrophy and destruction of the GI tract wall, and hence decreased absorption. Chronic pancreatitis, that's not the case. In chronic pancreatitis, you don't have the enzymes to degrade R protein, and therefore you can't free up B12, it can't unite with intrinsic factor, and therefore you get decreased absorption. So same end result, but two completely different mechanisms. Likewise, in chronic pancreatitis, you just aren't producing enzymes, so you're not going to produce pancreatic lipase anymore. So that's why the fat is malabsorbed. And in celiac disease, same as before. So the villous atrophy leads to malabsorption of fats as well. Now, as you can imagine, boards writers can come up with a lot of variants of questions similar to this. So having a good understanding of the basic underlying mechanism will pay dividends later. And finally, we have a few more important disease mechanisms that can result in the decrease in vitamin B12 uptake. So here we have atrophic gastritis, types A and B. And remember that atrophic means that metaplasia has already begun to occur, where stomach mucosa is beginning to get replaced by fibrous tissue. And what does this lead to? Well, eventually you're going to have essential substances not being secreted, like HCl, intrinsic factor, pepsin, and so on and so forth. So this again is going to lead to digestive problems, vitamin B12 deficiency, and megaloblastic anemia. And another take-home point from this discussion is the most common cause of atrophic gastritis is due to H. pylori infection. Secondary to that is going to be autoimmune and other things that cause chronic inflammation. Last, we have pernicious anemia. So who remembers what pernicious anemia is? So this is a disease entity where autoantibodies are directed against the parietal cells or intrinsic factor itself, thus causing a reduction in vitamin B12 absorption. So I think that's a good enough review for now. I hope that this was helpful, that you can apply it to patient care, to boards questions, to your teaching. And if you don't like it, please give it a thumbs down. But if you like it, hey, I'll take a thumbs up. Any feedback is always useful. So thanks again for joining. So long and goodbye.